Thank you, Ron. So I got really two simple points I want to make today, and I got a bunch of slides to help me do that. But the first one is this connection between water and energy. We've done a lot of focus on water, but the reason we're doing that is really because of energy. And the second point is going to be this connection between data and organizational culture. That you really need both to make this work and to achieve the results we've been able to achieve. So let me see. Okay, so before we get started, we're talking a little bit about climate change today, and Vermont has had 200-year floods in the last 6 months. So we really are starting to appreciate this relationship, and hopefully I can get this to play. No, that's not what I want to do. Can you play that video? Can you like double click on that? So this is the river. Just I think if you double click on it, hit it one more time. Nope, it doesn't want to play. This is the river right next to the IBM manufacturing plant, and this is the aftermath of hurricane and then tropical storm Irene, and this is one of our 100-year floods. And I grabbed a couple shots to just demonstrate in the natural world this relationship between energy and water. I particularly like this one on the left where you see the dog looking at his master, presumably. And I'm not sure if the dog is smarter or doesn't have the same sense of adventure that the master has. But I'm quite sure that if his master slips off that culvert, we're not going to see a Rin Tin Tin rescue. You know, the dog is going to let him go downstream. One more shot. You know, these are some of the major corridors. The one on the left there is the north-south corridor, state highway, that was just completely cut out by Hurricane Irene. And the two on the right are Route 4, which is a major east-west corridor across the state of Vermont. The point being is that there's this very direct link in the natural world and in the industrial world between energy and water. So what do we do in Vermont? We make chips, and we make chips for go into optical networks, into wireless base station communication satellites. A key thing in our business over the last decade is that none of our chips go into IBM products anymore. All of our chips are going into products like these, and as a result, we are competing on the global market. And as Anish said earlier, we're not going to be able to compete on wages in the global market. The way we compete in the global market is on intellectual property. This is a picture of our site. That river there, it was the same river that we saw earlier in a more behaved time frame. We use a lot of water, 3.2 million gallons a day. We use a lot of energy, 65 megawatts a day, peak power, and we collect a lot of data. We have about 60,000 data tags that are coming back into our SCADA systems, a subset of that rolling up into our PI system. So very quickly, I'd like to discuss data architecture. And this is a data architecture not only from a technical standpoint, but I also want to have you think a little bit about the cultural standpoint. Down below what we call level 0, level 1, level 2 are your typical data collection systems where you have sensors out there and you have PLCs and you're bringing all this data in. A lot of these are closed loop, and all these things are doing what they're supposed to do to control your processes and to make your site run. Where Pi comes in is in this level 4 what we start calling information. So here we're taking this data and we're trying to serve it out as information, and information that we can take actions upon so that we can improve efficiency, so that we can respond quickly to changes. And this information layer has allowed us culturally to start addressing silos of control in our business. So in our information layer, we have not only energy data, we have water data, we have chemical systems data, we have all of our HVAC data, we have all of our lighting data, all in this common database. And when you put all that information in the common database, you start addressing the silos of control inside your organization. You know, I should say the Burlington site has 5,000 people working there. So, and we have lots of organizational structures, but when we start going after energy, all of the 5,000 people are users of that energy, and we want to get this information shared across all of that. Now, on top of that layer, what we call our intelligent layer is where we've started building, you know, IBM applications, if you will, to extract the data from OSI Pi and start building advancements in how we use that data. On the left-hand side, we have asset management, where we're doing real-time maintenance based on data. We have started developing building optimization models to optimize the HVAC energy use. Our energy efficiency program, which really thrives on this information and data. A peak power management application, and similar to the University of California, who's looking at solar prediction, we're looking at temperature and dew point prediction, because that's the correlation that drives our demand. So we're taking that information and building a model that allows us to predict the right time to load shed. And then finally, we do statistical process control. One of the things in a semiconductor fab is that we have very tight control of our manufacturing processes. What we wanted to do was to take that tight statistical process control of the manufacturing process, move that into the water management world and the energy management world. Up on top is this idea of continuous improvement and culture. With all these tools down below, if you don't have the right culture and if you don't have the right people involved, and in our case it's everybody involved, it's hard to use these tools. Okay, so going on to water. How do we look at water? We look at water from supplier relations. We look at water. When we purchase water, we recognize we're not only purchasing water, but we're purchasing kinetic energy. We're purchasing pressure. We try to use that pressure to our best advantage. We look at efficiency. I'm going to show you on the next slide an example how we've optimized efficiency in the way we use water. Heat energy recovery. You know, again, this link between energy and water. Much of the energy that comes out of our semiconductor process, we transport into our water, to the tune of saving about $2.3 million a year in natural gas purchases. Manufacturing use efficiency. Wastewater treatment. A lot of the data we use goes to optimize our wastewater treatment processes. And you know, we have this stewardship of the resource. You know, we live in Vermont. Vermont is a very green state. IBM wants to participate in that green community in Vermont, and managing water correctly is a great way to do that. So this is an example of one of the algorithms that we built. And so, you know, on the bottom there we see, you know, the Pi data, which is, you know, looking at, you know, very simple algorithms showing efficiency of our RO treatment process. But on the right-hand side, in these tables are some very advanced mathematics that we're doing to optimize this unit treatment process. This is something that algorithms that weren't available in the industry a few years ago that we really spent a lot of time building. And then the key then is you need to serve that information up to the people who are running this process in a very informative and easy to understand way. So these algorithms allow you to present the results in a very easy to understand way so people can take actions on them, because those actions is what's going to drive our savings. And myself, sorry about that, myself as an engineer is not the person taking these actions. Our executives are not the right person taking the actions. The people taking the actions are the folks that are down at the ground level. Those are the folks that turn off the light switches, that save energy, that improve the efficiency of water treatment. So what have we done? So bottom line, this is our energy results over the last decade. If we look at the chart on the left, our water results for the last decade. In 2000, we were purchasing about 4.5 million gallons a day. Today, we're purchasing about 3 million gallons a day. The red line shows our manufacturing output. So what we see is about a 30% increase in manufacturing output from our fabricator in that same time frame. So we have driven our water usage down. As a result of driving the water usage down, we saved about $750,000 in water purchase cost. We saved about $600,000 in treatment cost, and we saved about $2.3 million in energy. At the same time, manufacturing has gone up. So if we would have made these savings, we would have made capital investments in water treatment infrastructure. So there's a cost avoidance here in capital expenses that is not really represented here. This is purely operational expenses. We've also worked on improving the quality of water that we discharge to the Winooski River, the same river that we saw in those slides. Phosphorus is a chemical of concern in our aquashed, and we look at the whole watershed. And Lake Champlain is concerns about nutrient loading in the lake. While we had a permit allowance up to the top of that graph, up to 1.2, we still knew it was a concern for the community, and we started going after reducing our phosphorus load. We reduced it by almost 50%. And at the same time, we found out we had reductions in fluoride loading, we had reductions in solids loading, and maybe more importantly to us as a business, we had some cost savings. $50,000 years in sludge disposal costs and $400,000 years in chemical usage. So oftentimes when we dig into these issues, whether we're going after water savings or energy savings, we're finding these related cost opportunities. And we're finding them because we're digging deep into these issues. Okay, moving on to electrical. We have 65 megawatts. We have been running what we have called a smart grid for more than a decade. What we call a smart grid is this idea of being to not react to usage, but predict what's going to happen with a smart grid, so that we can keep our fab running continuously. We look at power quality, extremely important in the semiconductor business. Fluctuations in voltage can cause our tools to go down. Load management, billing. Again, organizationally, culturally, how do you drive energy conservation through your organization? We do it by bills. We hand bills out internally in our site so that if a manufacturing operation has an energy bill, has an energy usage reduction target, and report up to the site executive once a month on their performance towards that. So again, this having the tools in place, but also driving the organization to respond to these targets. We look at energy efficiency, a lot of data, and when we identify projects, we have over 100 projects a year that we implement on energy management. How do we choose which ones to implement? Well, it's data analysis, it's cost-saving estimates, it's return on investment calculations. Again, a very data-intensive process. So a little bit on peak power. So on the right there was going back to 2005, we started correlating what's driving our electrical usage. We need to understand what are the aspects of running a semiconductor fab that drives electrical usage. So we did a lot of data correlation, and we finally ended up recognizing that one of our largest driver is weather. So we have this correlation on the bottom left there of the relationship between peak power in megawatts and the dew point of the air. So once we understood that, now we can start going after it. And the chart on the right shows our success. So year after year, we're able to drive down this curve. You drive down the number of megawatts that we use for a given outdoor air dew point and humidity. We get down to 2009, which is the lowest one. You see 2010 slightly higher. Well, in addition to dew point humidity, there was an economic downturn. So, 2009 was a kind of an anomaly just because of the economics and the productions of our fab. But this curve on the left had a very interesting upturn. So you see this thing kind of sloping down, but then it upturns. And we did more analysis on that this year to understand this bimodal correlation that was going on between dew point and energy. We're working on that this year to take better advantage of the opportunity we're losing, which is about 2.5 megawatts of opportunity that we're losing during the winter, and we're going to go after that strong this year. So how have we done on electrical consumption over the last decade? Our total energy use is down 20% over the last decade. At the same time, we had this manufacturing uptick of about 30%. The way we achieve this is that we're setting goals each and every year. Every year we are setting new goals for energy opportunity as a minimum of 4%. In years like 2009, when we had an economic downturn, we've set site targets at 6 and 7% reduction. Okay, so culturally, how do we really attain that kind of sustained performance year after year after year? After you pick all the low-hanging fruit, how do you keep driving performance? And the way we do that, and it's an overview of energy, but water would be similar, is that at the bottom, every employee in our site has an expectation to contribute to reducing energy. It's in all of our objectives for the year. We have department representatives, we have a conservation team, and I mentioned earlier we hand out bills. So each of these department representatives are getting an energy bill. As Byron said, if you can't measure it, you can't manage it. And that measurement needs to go down to the people who use the energy. For me to measure it and understand that a given department is using a lot of energy is not as effective as the department manager understanding that he's using a lot of energy or she's using a lot of energy, and it's not consistent with the goals that they're trying to get that year. And then the senior location executive, once a month, we have a site of 5,000. Energy ideas and performance roll up to our site executive. And the site executive is looking at that performance and saying, are you on track? If you're not on track to meet your targets, where is the money going to come from those energy savings that we booked, that we were counting on? So it puts this economic pressure on the operation managers to drive energy performance. In addition to the bottom line of saving dollars, saving energy and using less water, we have recognition in the environmental community. If you see in 2007, the National Pollution Prevention Roundtable has recognized both our water conservation programs and our energy conservation programs. We continue to get government, state of Vermont, governor's awards for our performance in this area. The bottom line is that, aside from the economic benefits we received, there's a good neighbor corporate social responsibility benefit to having programs like this. So I'd like to just spend a few minutes talking about the things that we're doing now, the new stuff that we're doing with ourselves and with OSI. And IBM has this really nice asset management tool called Maximal. And what Maximal does is say, when do I need to do maintenance, and tracks maintenance and connects to purchasing and crib parts and all kinds of things like that. But what we really want to do was to take Maximal and have it being driven by the data that's sitting in our Pi historian database. So, what are the triggers? I only need to do maintenance when the equipment tells me I need to do maintenance, not because it's January and we always do the maintenance in January. So, and this, not that this is really groundbreaking. People have been doing this for quite some time, but the reason we did this demonstration project with OSI was to be able to kind of push this out to the bigger IBM. I live in IBM Vermont in our little semiconductor world, but to push this out to the bigger IBM so that they can go out and start leveraging this connection between data and maintenance to drive sales for Maximal and also for OSI. And this last project is something I'm leading up, which I'm really excited about, is Vermont is building a smart grid. So Vermont was granted federal funds to start building and developing a smart grid. OSI stepped up to the plate about a year ago to help us build this alliance. And what we want to do in Vermont is that there have been some smart grids across the nation that have got started and really didn't really, I don't want to phrase this, maybe meet the promise that the population expected, that the people expected from the smart grid. So Vermont, getting on to build a smart grid, we wanted to make sure that wasn't going to be the case in our state. And we came up with a concept of taking our energy management program and pushing that out into the state. So ourselves, OSIsoft, we have our power utilities, we have some controls integrators, and we have a whole list of businesses across the state of Vermont. We have mining interests there, we have Cabot Cheese, we have some ski slopes, hospitals, and the idea is that how do we help, once this data becomes available, the user data that the smart grid promises, what are people going to do with that data in order to drive efficiencies in energy usage, which drives efficiencies in distribution and transmission of energy. So starting this month of November, all these companies have agreed to send their data to an IBM server. We have OSI software loaded on a server. We're going to be aggregating this data. The analysis that we've been learning for the last decade on analyzing IBM data, we're going to start applying to all these different companies and pushing that information back out. And the hope is that once we push that information back out, they'll be able to drive down their energy usage. The utility, on the other hand, in about 2 years, they're going to start having their own smart data flowing into the utility. And the utilities have the same question. Well, we could send out just usages. This is how much energy you use on a 15-minute interval and give that to the user. But what can we do with the data analytics? How can we take that data and optimize voltages in substations, optimize the distribution system, help all of the utilities customers use energy in a quote-unquote smarter way. So this is my last slide. So that will be it then. Oh no, I'm sorry, it's not my last. Okay, This is important. There's a little bit of icons on here, but I think this is really important. And I really want people to maybe walk away with this one. This idea that it takes two. You know, on the top I have some icons there of the way things were a decade ago with silos of information. You know, from leaders, business leaders in your organizations, you need to say, if you have silos, you want to get people to, I love data, and I want to contribute my piece of data to the big puzzle. Down below, we have the data analytics. You know, we have the data geeks, we have the people who love, building algorithms, looking at the data. And you really need both of those things to make this whole thing work, because either one unto itself doesn't have the power of both. So I encourage you to commit to both. Thank you.